6.1 Embeddings and Euler's formula. So, in this section, we're going to go ahead and introduce the concept of a planar graph. In particular, one big theorem that we're going to be talking about today is Euler's formula, which sort of serves as a nice way to verify if we have a planar graph. Of course, there are some other cases that we will have to consider, but it's one of the ways that we can consider a planar graph. So, to start us off today, before we even talk about the definition of a planar graph, it's important that we have some background on this. So our first definition for today, a curve is the image of a continuous map from 0 to 1 to r squared, or r2, however you want to say it. In other words, if I have the line segment 0 to 1, a curve is a transformation of this line segment. That is, I can take this line segment from 0 to 1, and then I can do some type of transformation on this line segment, such that after I apply this line transformation, let's call the transformation f. First off, 0 goes to f of 0, and 1 goes to f of 1, and everything in between can be modeled out in some type of way, like what I have here. So remember that R2 is just, you can think of this as a way of saying our two-dimensional space, or you can even think of this as our xy Cartesian plane. We're taking a one-dimensional number line and transforming it and mapping it onto our R2, our two-dimensional space. So we have a curve. The next definition I have for y'all is a polygonal curve. A polygonal curve is also a curve, well, as you probably guessed from the name, but instead it's composed of finitely many line segments. And remember that we consider a line segment to essentially be, you can think of this as a straight line. So what I have here on the right, this is not a polygonal curve. It's still a curve, but it's not polygonal, because clearly we do not have a union of straight lines here. Instead, a polygonal curve might look something like what I have here. You can see here that each part of my curve consists of straight line segments exclusively. So we have a polygonal curve. And if I want to be exact, I could say a polygonal UV curve. This is just a polygonal curve where I start at the point U and I end at the point V. Very similar to whenever we talked about a UV path. Last thing I want to introduce here is a closed curve and a simple curve. A curve is closed if its start and end points are the same. So I start it at, let's say, U, then I must also end at U as well. Lastly, a curve is simple if it has no repeated points. That is, I don't cross over myself along this curve. So for example here, I have this polygonal curve, and I can see that it overlaps. It crosses itself. Hence, the curve I've drawn here on the right is not a simple curve. In fact, it's not a closed curve as well. So we have some base definitions of a curve. So what are we going to do with these definitions? Well, again, we can finally now introduce the definition of planar. What does it mean for a graph to be planar? So, a graph G is planar if there exists an embedding on R2. Or more informally, we can say that where a graph is planar if I can redraw my graph G in such a way such that no two of its edges cross each other. Again, or I can think of this as if all of my edges, or all the edges of my graph, can create a simple curve in a sense. So a planar graph G partitions my plane, my two-dimensional space, into separate non-overlapping areas, which we're going to call faces. And then whenever I talk about a face, I'm going to want to talk about the boundary of the face, which is just going to say these are the edges that create the border, or you can say even the outline of the face. And as you'll see in just a moment whenever I bring up an example, the faces that are bounded by edges of G, we're going to split up into what we call our inner faces versus our outer unbounded face. So, for example, I showed it a little prematurely here on the right, but here on the left I have K4. my 4-click, or you might call it that. This is my complete graph on 4 vertices. So I claim that this is a planar graph. Well, you might be looking at this and say, well, how is that possible? Because these two edges are crossing each other. And I agree. These two edges are crossing each other in the middle. However, remember our definition says a graph is planar if we can draw it in such a way, such that no two edges cross each other. So even though initially these two edges are crossing, it is possible for me to redraw this graph. Let's say I take this diagonal edge that goes from the bottom left to the top right. You can imagine that I pick up this edge and then stretch it over to the top left. That is, for example, I can draw it such as what I have here. If I draw in this way, I still have all of my same edges, but they're just drawn in such a way that no two edges are crossing each other now. Hence, my graph is in fact a planar graph. So I have this here. Now let's talk about that definition of faces. So if I look at this planar graph, I can imagine that it's split down and partitions my two-dimensional space into these distinct areas that are enclosed by the edges. So for example, if I look at this top right triangle, that's one face. I'm going to call it F1 for face number 1. And then I can label this next one F2, this next one F3, and then the rest of this F4. So if I look at F1, F2, and F3, I call these my inner faces. These are the faces that are bounded within my graph. On the other hand, F4, this is an unbounded face. It's not within my graph, but it's still a face. We call this our unbounded face. That is the exterior face, or even we might say the outer face. Generally speaking, we only have one outer face whenever we're looking at these graphs. So we have our concept of planarity in our graphs now. So this idea of planarity actually brings out a lot of nice results, because planarity is actually a pretty big restriction on our graphs. So some things that we need to talk about that go alongside with planarity. So this next theorem I have, this one's not necessarily just planarity, but can be applied in general. Theorem 6.1.1. This is actually called the restricted Jordan curve theorem. So if you've done some work, possibly in analysis or complex analysis, complex variables, this theorem might sound a little bit familiar. And this is a little bit of a simplified version, hence the word restricted Jordan curve theorem. A simple closed polygonal curve C that consists of finitely many segments partitions the R2 plane into exactly two faces, each having C, my curve, as the boundary. In other words, if I have a polygon, here I have a closed polygonal curve that's also simple. And we can double check and make sure that what I've drawn here does match all of my conditions. Is it simple? Yes, I don't have any edges crossing each other. Is it a polygonal curve? Yes, it's consisting only of straight line segments. Is it closed? Yes, I can pick any start point, and then eventually if I follow my curve, I end up at my original start point. So I do have a simple closed polygonal curve. So if I look at this polygonal curve that's simple and closed, you notice that it actually just forms a polygon. And this polygon can divide my R2 space into two faces. That is my inner face, we can call it F1, and then we also have our outer face, that unbounded face. So looking at this might seem a little bit obvious, but actually it does take quite a bit to actually prove this result. And unfortunately, we won't be going really into the proof of this theorem. Just know that it's not as simple as what the picture I've drawn here. It does take a fair bit more background for us to actually prove this. All right, so we have this restricted Jordan curve theorem. The next thing is now talking more about planarity. There are two graphs in particular that I want to talk about being non-planar, that is not planar. So for our proposition 6.1.1, the two graphs K5 and K33 are not planar. So remember, K5 is the complete graph on 5 vertices, which looks like this right here. I have 5 vertices, complete graph, meaning each vertex is connected to all of my other vertices in my graph. And remember that K33? This is my complete bipartite graph. This is the graph where I have 2 independent sets of size 3, such as what I have here. So here I have 3 vertices and another 3 vertices. Every vertex on the left is connected to each vertex on the right. However, I must maintain that the 3 on the left are independent of each other, that is, they are not connected. So these 2 graphs in particular are not planar. One quick thing I want to notice, why did I bother mentioning these 2 particular graphs? Clearly, these are not the only non-planar graphs. But as it turns out, we actually use these 2 specific graphs to show and help us figure out planarity of any given graph. We're going to find out, actually, I believe in either this video or the next video, if I contain a K5 or K33 subgraph, then I know that my overall graph is not planar. And just to be very clear, we know that this is not planar also because no matter how you redraw this K5, there is no possible way for us to redraw this such that no 2 edges cross each other. You can try if you want, but you're going to end up with at least one pair of edges that cross each other. If I want to be a little bit technical, this is applying for whenever we're working on R2 space, that is our flat 2-dimensional space. There are some weird things that you might read about if we work on different topological surfaces like a torus, that is a donut, or stuff like that. But we're mainly just working on our standard 2-dimensional space. All right, so this is our proposition. Just some other definitions and notations that we should be familiar with when we talk about planarity, in particular about faces. If I have a planar graph G, if I use the notation capital F of G, I use this to represent the set of faces of G. This is sort of the same idea as the vertices and edges. Remember we said big V of G, that was our set of vertices. Big E of G, that was my set of edges. Well, here big F stands for my set of faces. So if I have a face, or let's say an edge is incident to a face F if that edge is part of the boundary of F. And then the length of my face, here this should be a capital G, that's a typo on my end. That should be L capital G of F, or just L of F, is the number of edges incident to F. So let's say I have this graph right here, and I consider this internal face, the inner face that's being enclosed by these edges. So if I look at this inner face is incident to this edge, and this edge. So we're incident to 3 edges. Hence, my inner face has length 3. So this is how we think about the length and an incidence between an edge and a face. So moving from here, more definition. I know I'm drawing a lot of definitions at y'all, but planarity is such a big topic and something really interesting for us. The dual graph, I call this G star, of a plane graph, or planar graph, is a planar graph with the vertex set V of G star is equal to F of G. In other words, the vertices of my dual is the same as the faces of my original graph, such that to determine if 2 vertices of G star are adjacent, they're adjacent if and only if their corresponding faces share an incident edge. Now, what does that mean? So let me pull up this example here. So on the left, I have this graph G. This is clearly planar, and I have 3 faces, F1, F2, and then my outer unbounded face F3. The dual graph says, let each face become a vertex. So notice on the right, I have F1 is a vertex, F2 is a vertex, and F3 is a vertex as well. So if I look at this, F1 and F2, they share a common edge, this middle edge right here. Hence, they must be adjacent. I'm trying to trace these as cleanly as I can with my mouse. So that's why we have this edge over here. But what about F1 and F3? Well, F1 and F3, we have this edge and we have this edge. So we have two edges that they share. Hence, F1 and F2 in a dual must share two edges between them. And then we pretty much have the same thing for F2 and F3. If I look at F2 and F3, they share two common incident edges. Hence, there are two edges between F2 and F3. Notice here that my dual could be a multiple edge graph. That is, my dual graph does not need to be a simple graph. So that's something to be careful about. So just a very nice thing on a dual graph. This is a similar idea to, remember way back then we learned about a graph and its complement. As it turns out, just how before, sometimes it was easier to consider the complement of a graph. Sometimes it's easier for us to consider instead the dual of a graph, depending on what we're looking for. So now let's finally go ahead and talk about our major theorem for this video. I want to talk about Euler's formula. And I know depending on which mathematician you talk to, they may give a slightly different pronunciation. To my knowledge, I've always called it Euler's formula instead of Euler's formula. And this was actually quite a while back, a very old result, 1758. So if G is a connected planar graph, then the number of vertices minus the number of edges plus the number of faces is always equal to 2. So it seems a little bit odd that no matter how many vertices, edges, and faces, they have this relationship that they sum in difference up to 2. So let's go ahead and provide a little bit of a proof on how this is proven. So the way that I'm going to choose to prove this, note that there may be multiple ways that you might prove this, is I'm going to do this by induction, particularly on the number of vertices. So just for convenience, let's go ahead and let n be the number of vertices in my graph. So remember, for a proof by induction, I generally split this into two cases, or two parts, the base case and then my inductive step. So for a base case, let's go ahead and start with n equals 1. That is, what if I have a graph with a single vertex, such as what I have down here. Here I have a single node or a single vertex, whatever terminology you prefer. And I have to consider a couple of things here. First off, if my edge set has size 0, that is, I have no edges in my graph that has a single vertex, then there must only exist one face, that is the unbounded face. I have no inner faces here. That tells me, hence, that the number of vertices minus the number of edges, and this should be plus the faces, that's my mistake, is equal to 1 minus 0 plus 1 equal to 2. So again, I had one vertex minus my 0 edges plus the single one face that I have on this graph, like here. So clearly 1 minus 0 plus 1, I get 2. Thus, for the base case, we're done. But what happens if I do have an edge? Well, if I do have an edge in this graph, I only have one possibility. Since there's only a single vertex, I must have a loop here. So if I have the number of edges is 1, my only possibility is that I have a loop. And that's still fine. This graph is still planar, and I never said that my graph has to be a simple graph. I just said that it has to be planar. So if I have a single edge in here, let's see how many faces do I have. Well, I have this one inner face, and then my same outer bounded face. So I have two faces in this case. What if I add another loop? If I add another loop, then all that does is add one more face to my graph. So if I have 2 loops, I have 3 faces. You can imagine that if I added a third loop, then I have 4 faces total. So more formally speaking, if my edge set has size 0, then the edges of G must consist of a finite number of loops. In particular, like I said, the first loop makes 2 faces, and for each loop I add, I get 1 extra face. That is, the number of faces is equal to the number of loops plus 1. So if I substitute this into my original formula here, the number of vertices minus the number of edges plus the number of faces, this is in particular equal to, we had 1 vertex, minus the number of edges, plus, and we just said the number of faces is equal to E of G plus 1. So if I clean this up, I should end up with exactly 2. Thus, the theorem does hold for whenever n is equal to 1. We are done with our base case. But remember, for an induction proof, I have 2 parts, the base case and then my inductive step. So I proved this only for n equals to 1. What about n equals 2, 3, 4, any whole number that's positive? So let's continue from there. Let's do our inductive step. Our inductive step says, assume the theorem holds all the way up to some fixed number n. We don't know what that number is, but we can assume it works up to some fixed number. And now let's consider a graph with exactly n vertices. As G is connected, then we know there must exist at least 1 non-loop edge E. So again, I'm assuming I have more than one vertex. And since I'm connected, those edges had to be connected to each other, or those vertices must be connected to each other. And hence there must be at least one edge that's not a loop. It must be between at least 2 different vertices. So the way that we're actually going to do this is, let's go ahead and consider G contract E. Remember that it's G dot E. That means I took the graph G and I focused on one edge and I contracted it. That is, I made it into a single vertex point. So using this, the number of vertices in the contraction, we lose 1 vertex. That is, the number of vertices in my contraction is the number of original vertices minus 1, so n minus 1. And the number of edges is going to be equal to the E of G minus 1. Again, whenever I contract an edge, I lose a single edge. So, as the contraction of E does not reduce the number of faces, again, this is another typo on my part, we should have that the number of faces in my original graph is equal to the number of faces in my contraction. Hence, by induction hypothesis, since I have strictly less than n vertices, I have this here. The number of vertices in my contraction minus the number of edges plus the number of faces is equal to 2. But using these equalities, remember the number of vertices in my contraction is the original number minus 1. The number of edges is the original number of edges minus 1. And the number of faces is the same. So if I clean this up, let's see, I have plus 1 minus negative 1, giving me negative 1 plus 1. So these ones form a 0 pair, leaving me with this formula here, which is exactly Euler's formula, which is what we wanted to prove. Thus, the theorem holds for all natural numbers n, completing our induction step. So we just proved that given any planar graph, let me scroll back here. If we have any connected planar graph, then I must have this equality hold. In other words, if I gave you the number of vertices, the number of edges, and the number of faces, you can tell me immediately if it's planar or not, or if it could be planar, or if it's not planar. So we have this here. So that's Euler's formula, very major result and very commonly used theorem whenever we're talking about planar graphs. All right, so that's all for this video. There were some definitions that I did not cover in this video. So again, I do recommend that you look over the notes for those little extra tidbits and extra theorems that were there. But besides that, I'll see you in the next video.